Imagine a trillion parameter AI model trained on literally all of human knowledge, just completely ruining a physics experiment.
Oh, yeah, just tanking it.
Right, like because it forgot to convert Celsius to Kelvin and just kept marching forward without even checking its work.
Which happens way more than you'd think.
It really does. Welcome to AI Paper Slop. Today we are dissecting the paper Deep Research in Physical Sciences, a multi-agent framework and comprehensive benchmark.
It's a fascinating read.
It really is. So here is the core takeaway right up front. Generalist AI agents are hitting a massive wall in complex scientific reasoning.
A very hard wall.
Yeah. State-of-the-art models like Gemini Deep Research, they're scoring a dismal 33.5% on real-world physics and chemistry tasks.
Which is shockingly low.
It is. And this paper reveals exactly why they fail, mostly cascading planning and execution errors.
Right.
But it also introduces a solution called DelveAgent. It's this specialized multi-agent framework equipped with adaptive planning, dual-granularity memory, and physics-grounded reflection.
And the results are actually pretty wild.
Yeah, it boosts accuracy by 7.5 percentage points while cutting inference costs to just 1/3 of the baseline.
A third. That's huge.
So if you are an AI researcher or machine learning engineer building agentic workflows, this episode explains why scaling generalist models just isn't enough for specialized domains.
Exactly.
And how targeted architectures drastically improve reliability and cost efficiency. Let's get right into it.
We really are looking at a fundamental shift here, I think. The underlying premise of this paper challenges that whole, scale's all you need mantra.
Right. The idea that bigger is always better.
Yeah. That idea that just adding more compute and more data fixes every reasoning problem, it completely breaks down when you enter the rigorous, highly structured world of the physical sciences.
Well, before we talk about how the authors fixed the problem, we kind of need to understand how they measured it.
Which is a whole saga on its own.
Yeah, reading through the paper, they essentially argue that existing scientific benchmarks are fundamentally broken for real-world research.
They do pull no punches there.
And I'll be honest, my first reaction reading that was a bit of skepticism.
Really? Why?
Well, don't we already have massive chemistry and physics benchmarks? Like, we have the Humanities Last Exam, HLE, and things like PhySciBench or Frontier Science.
Sure, we do have those.
Right. So building an entirely new benchmark from scratch is a massive, expensive undertaking. Why not just use what's already out there?
It's a very healthy skepticism, actually. And any ML engineer should ask exactly that question before just, adopting a new metric or abandoning an old one.
Right.
But to understand why those older benchmarks fail here, you have to look at how they are structurally designed. They evaluate isolated single-turn tasks.
Okay, so just like one prompt, one answer.
Exactly. Or, in the case of something like PhySciBench, the tasks are almost entirely text-based. It asks a text question and expects a text answer.
Which isn't real life.
No, not at all. Think about the day-to-day reality of an actual physical scientist. Your workflow isn't just answering a multiple-choice question about some concept from a textbook.
Right. I assume a real workflow involves, pulling up a dense research paper.
Oh, absolutely.
Looking at a highly complex graph, maybe writing a Python script to extract the data points from that graph.
Yep. And then maybe running a physics simulation based on those exact points.
Right. And then synthesizing a conclusion at the end of all that.
Exactly. Real scientific inquiry demands multimodal parsing, structured data extraction, and actual code execution.
All working together.
And crucially, all of those steps have to be chained together seamlessly. If your agent fails to parse a data table accurately at step 2,
then the simulation it runs at step 5 is just completely useless.
Exactly. It's garbage in, garbage out. That extended multi-step reality is what existing benchmarks completely miss. And it's exactly why the researchers built PhySciBench.
Okay, so what does that benchmark actually look like under the hood? How do you test for that multi-step reality?
Well, they built it from the ground up. It consists of 200 expert-curated questions, and they split it evenly down the middle between physics and chemistry.
Nice and balanced.
Yeah. And the design goal was to evaluate those extended workflows across 3 distinct cognitive stages.
Okay, what are they?
Information extraction, scientific understanding, and finally, application and creation.
So it's not just, do you know this scientific fact?
Right.
It's, can you find the fact in a dense paper, actually understand what it means, and then use it to build or simulate something new?
Yes, and they broke those 3 stages down into 6 specific task categories
Yeah.
just to make the evaluation super granular.
God.
You have multimodal QA, structured information extraction, long context QA, scientific reasoning, experimental design, and code generation.
Wow. So it essentially mirrors a day in the life of a principal investigator in a lab.
It really does. It's a full stack evaluation.
One thing that always concerns me, though, with new benchmarks is data contamination.
Oh, the dreaded benchmark leakage.
Yes. We've seen so many instances where models score like 99% on a new test, only to find out the test was accidentally included in their pre-training data scrape.
Right, just regurgitating.
Exactly. It's essentially an open book test where the model has already memorized the answer key. So how does PhySciBench avoid that?
That is actually a massive selling point for this benchmark. To guarantee zero contamination, the domain experts who built PhySciBench, they authored the questions directly.
Okay, so no web scraping.
Right. They didn't just scrape public data or Wikipedia.
Yeah.
They took recent high-impact papers, and we're talking really niche publications from just the last 5 years,
Oh, wow.
along with authoritative textbooks, and they fundamentally reformulated the problems. So a simple string match retrieval won't save the model here.
It actually has to reason through the novel formulation.
Exactly.
That sets up a pretty brutal gauntlet for these models.
It really does.
And once PhySciBench was locked in and validated, they ran the absolute best generalist systems on the market against it. And the results were,
Honestly, a bloodbath.
a bloodbath. Gemini Deep Research, which most people consider the absolute gold standard for agentic research right now, achieved only 33.5% accuracy.
Which is just staggering.
And when they tested models like Gemini 3 Flash or Grok 4.1 Fast, the scores dipped completely under 30%.
Yeah, the low scores are alarming on their own, but what's really fascinating is the context.
Right.
These reasoning-enhanced systems, the ones utilizing advanced chain-of-thought processing that absolutely dominate standard leaderboards.
The ones that are supposed to be the smartest.
Right. They still belonged. It empirically proves that standard chain of thought is just insufficient for the physical sciences.
But the researchers didn't stop at just reporting that benchmark score.
No, they did a really comprehensive postmortem. They isolated 326 verified failure cases from Gemini Deep Research to figure out the exact mechanisms of failure.
This part of the paper is an absolute goldmine for anyone actively building agents right now.
Oh, it really is.
They categorized the failures into 3 distinct buckets. The largest bucket, making up 46% of the errors, was planning and reasoning failures. And from what I understand, this is an issue with unstable long-horizon reasoning. Like, the agent makes a tiny interpretation error at step 1.
Right.
But because it never pauses to reassess its trajectory, that error cascades, and the final output is just complete garbage.
It basically commits to an initial plan and just marches blindly forward, completely ignoring the intermediate signals it receives.
Like it has blinders on.
Exactly. Imagine an agent tasked with calculating the boiling point of a newly synthesized polymer, right? It writes a script to parse a data table.
Okay.
The script runs. But because the PDF formatting is weird, it extracts empty variables. Now, a human would stop and say, wait, let me look at the source table again.
Yeah, obviously.
The agent, however, just passes those empty variables to the next step, which causes the math equation to fail.
Which causes the final conclusion to confidently hallucinate a temperature.
Exactly. Just totally made up.
Wow. Okay, so the second bucket, and this accounts for 31% of the failures, was execution and response. These seem more like mechanical breakdowns rather than logic failures, Tool chain timeouts, failing to process a complex PDF document, or violating strict formatting constraints.
Yeah, it's the agentic infrastructure just failing to deliver the payload.
Right. But in a scientific workflow, a formatting error can be just as fatal as a logic error, right?
100%.
Yeah.
If an agent is asked to output a strictly formatted JSON array representing chemical bonds, to feed into a simulation tool, and it includes conversational text because it's safety alignment or its helpfulness tuning kicked in.
Like, here's the JSON you requested.
Exactly. That downstream simulation script instantly breaks, it just crashes.
Unbelievable. And then there's the final bucket, which is 23% of the errors, knowledge, and implementation.
Yeah.
This is where the agent flat out hallucinates a chemical mechanism or completely botches a well-known physics equation.
Just mix it up.
And the paper suggests this happens because the agent fails to transfer prior problem-solving experience to the current step.
Right.
So it's like watching a really smart undergraduate who memorized the entire textbook, right?
Yeah, perfect analogy.
But the second a piece of actual lab equipment breaks, they freeze. They ruin the entire experiment because they don't know how to step back, replan, and apply their textbook knowledge dynamically to a messy real-world problem.
That is exactly it. And if we look at the bigger picture here, these specific failure modes prove that the performance ceiling we are seeing in scientific AI is architectural.
It's not just a compute issue.
No, it is not a scale issue at all.
Yeah.
Throwing another trillion tokens of compute in the model will not magically teach it how to dynamically recover from a broken Python script in step 4 of a 12-step physics problem.
Right.
The agents lack dynamic recovery and they lack real scientific grounding.
Which brings us to the core framework they built to actually solve this, DelveAgent.
Yes.
It's a custom modular multi-agent system. And what I love about this is how directly it maps to the problem. Like, they built 3 core modules and they address those 3 failure buckets perfectly, one-to-one.
It is very elegant.
Let's break down how they actually operate.
Okay, so to fix that massive 46% bucket of planning failures, they introduced the adaptive planning loop.
Okay, how does that work?
Think of it like a principal investigator managing a team of frantic grad students in a lab.
Okay, I love that image.
Instead of the PI writing a rigid plan on Monday and just ignoring everything till Friday, the central planner agent dynamically dispatches tasks to specialized worker agents.
So the workers are the grad students going off to execute the subtasks?
Exactly. The workers go off and execute, but the planner constantly looks at their intermediate observations.
So it's checking their work.
Right. If a worker hits a snag, say, a data set they parsed doesn't contain the expected physical constants, the planner doesn't just let them keep going.
It stops them.
It dynamically revises the trajectory and replans on the fly based on that specific failure.
So no more marching blindly off the cliff.
Exactly.
Next, to fix the 23% of failures related to hallucinated knowledge, they built a dual-granularity memory system.
This part is so cool.
It really is. It acts as a shared memory bank accessible by both the planner and the workers. And it's split into 2 parts.
Right.
The first is the knowledge store. This seems pretty straightforward. It's your static, factual data, equations, standard scientific procedures, physical constants, essentially the textbook.
Yep, the textbook.
But the second part is the experience store. How does that actually differ from just having a database of facts?
Well, if the knowledge store is the textbook, the experience store is the stained lab notebook filled with crossed-out mistakes and margin notes.
Oh, that's a great way to put it.
It is totally dynamic. It stores successful past trajectories, recovery strategies, and specific planning patterns.
So it's learning from experience.
It essentially gives the agent the street smarts of a seasoned lab technician. For instance, it allows the agent to recognize, I've seen this specific type of pandas data frame error when parsing spectroscopy data before.
Oh, wow.
Last time, the fix was to adjust the dimensional array, not rewrite the entire extraction logic. It provides behavioral context, not just raw facts.
So it's remembering how it successfully solved a problem in the past, not just what the final answer was.
Exactly.
That drastically reduces hallucination because the agent isn't trying to invent a brand new method from scratch every time it encounters friction.
Precisely. It can lean on what worked before.
Okay. And finally, to address the 31% of execution and formatting failures, they implemented hierarchical physics-grounded reflection.
Yes, the reflection module.
So this is a 2-tier verification system. You have a local verifier checking step-level math, units, dimensions, and code execution in real time.
Right.
And then a global critic looks at the whole trajectory, checking source grounding and overall scientific consistency before the final answer is actually outputted.
That's the architecture, yeah.
Now, I have to push back here.
Okay, lay it on me.
I want to really drill into this because my team deals with API costs constantly. For an ML engineer building in the real world, API calls, token generation, and compute time equal money.
They absolutely do.
Doesn't constantly verifying units, running a separate local verifier, triggering a separate global critic agent, checking dimensions, querying dual memories. Doesn't all that make this framework incredibly slow and computationally expensive?
It's a highly intuitive concern, really. I mean, if you add multiple layers of verification and multi-agent back and forth, the natural assumption is that your inference latency and cost are just going to skyrocket.
Right.
But the empirical data in the paper shows the exact opposite is true.
Wait, really? The opposite?
Yes. By catching errors early at the local level, the adaptive planning loop prevents the agent from running down incredibly expensive long-horizon dead ends.
Okay, I understand the theory. Catching an error at step 2 saves you from running steps 3 through 10.
Right.
But does that really offset the cost? Isn't there a massive latency overhead in triggering a separate agent every single time you want to check a step? Like, how does the math on those API calls actually balance out to a lower overall cost?
The math balances out because of the nature of how generalist models actually fail. When a generalist model like Gemini makes a mistake early on, it doesn't just fail quickly and quietly.
It goes off the rails.
It hallucinates massive, complex, and entirely wrong answers. It will confidently generate a 500-line Python simulation that is fundamentally flawed, consuming maximum output tokens in the process.
Oh, wow. I see.
DelveAgent's local verification is actually a very lightweight API check. It course corrects early and then utilizes the past trajectories from its experience store to find the most direct path to the solution.
So it skips the hallucination phase entirely.
Exactly. The verification acts as a guardrail that prevents massive token-wasting excursions.
Ah, I get it. It's the difference between paying a small toll to stay on the correct highway versus driving 50 miles in the wrong direction and having to pay for the gas to drive all the way back.
That is exactly it. The extra API calls for verification are literally pennies compared to the dollars wasted on generating a massive hallucinated 12-step output that you can't even use.
That makes a lot of sense. So if this local verification is saving us compute by preventing dead ends, that should theoretically reflect in the final benchmark scores and the actual operational costs.
Right.
Did they actually see those cost reductions when they ran DelveAgent on PhySciBench?
They absolutely did. The numbers here are fantastic. DelveAgent hit an overall accuracy of 41.0% on the benchmark.
Nice.
That is a solid 7.5 percentage point increase over the Gemini Deep Research baseline.
And looking at the specific task categories, the gains are really pronounced in areas where the architecture was specifically targeted.
Oh, definitely.
Like in structured information extraction, DelveAgent improved by 15 percentage points.
Huge jump.
In code generation, it saw another 15 percentage point bump. And going back to that cost concern, DelveAgent achieved these results at roughly 1/3 the inference cost of Gemini Deep Research.
It's incredible.
Getting a 7.5% bump in cutting-edge autonomous scientific research is a massive win. But doing it at 1/3 of the cost, that's the kind of return on investment that makes ML engineering teams rethink their entire tech stack.
It is a remarkable efficiency gain, no doubt. But to truly prove that these architectural choices were the actual driving factor behind the gains and not just, prompt luck,
Right.
the researchers ran a rigorous ablation study. They systematically removed components to see exactly what would break.
I always love a good ablation study. It's the only way to really know if your fancy new module is actually doing the heavy lifting or if you just got lucky.
Exactly.
What actually happened when they started taking pieces out?
Well, when they removed the dual granularity memory, overall performance dropped by 3.0 percentage points.
Okay, a decent drop.
But if you look at how the system failed without it, it's very revealing. Without the memory supplying those tested format templates, the agent suddenly started making massive schema errors.
Like formatting issues.
Yeah, it literally forgot how to format its JSON outputs properly because it didn't have that experience store to lean on.
It lost its street smarts.
Precisely.
Oh.
Then, removing the hierarchical reflection caused another 3.0 point drop.
Okay.
Without the verifiers, the system just started letting basic, catastrophic unit conversion errors slip through to the final answer.
Oh, brutal.
And taking out the adaptive planning loop dropped performance by 2.5 points, specifically tanking the code generation scores.
Why the code generation?
Because without the loop, the agent couldn't iteratively debug. It would write a script, get a syntax error, and instead of fixing the syntax, it would just blindly hallucinate a result.
So every single piece is actually pulling its weight.
Absolutely.
Interestingly, the paper notes that removing all 3 components simultaneously dropped the overall score by 6.5 percentage points.
Right.
That tells me there's some partial redundancy built into the system. Like the modules actually compensate for one another to some degree.
Yeah, they work as a cohesive unit.
But without them, you are basically right back to the baseline generalist performance.
That's exactly right. The architecture is the differentiator here.
Hmm.
Now, benchmark numbers are great for papers, but the true test of a framework like this is a real-world application.
For sure.
So they brought in domain experts to design open-ended research tasks to see how DelveAgent would handle them in the wild.
Let's talk about study, too, because I feel like this perfectly illustrates the mechanics of the system we've been discussing.
It really does.
The open-ended task was to numerically reproduce a core finding for the 1D Flow-Majorana alpha chain model, often called FMAC, under strict parameter constraints, and then generate runnable code for it.
Which is a highly complex, incredibly niche physics problem.
Right.
In the execution trajectory, DelveAgent's document worker successfully extracted the theoretical structure from the source material. But during the initial implementation phase, the worker agent made a critical error.
What did it do?
It used fractional winding indices in the simulation.
Okay, for the ML engineers listening who might be a few years removed from their last quantum physics class, we probably need to explain what that means.
Good call.
Using a fractional winding index in this specific context is a massive red flag. It fundamentally violates the underlying physics of the FMAC implementation.
It completely breaks the rule.
It's essentially like trying to build a physical mechanical clock using half a gear. It simply cannot work in reality. The laws of physics don't allow for it.
That is a perfect analogy, honestly. Now, a standard generalist model would not catch that nuance at all.
It would just keep going.
Yep, it would push that impossible half-gear design through its processing pipeline, run the broken math, and confidently present you with a completely hallucinated simulation.
But DelveAgent caught it. How?
Because of the intermediate observations and the reflection modules, the system flagged the fractional winding indices as a physical violation.
Wow.
That immediately triggered the adaptive planning loop, which halted the worker agent.
It just shut it down.
Yeah. The planner stepped in, directed the worker to revise the FMAC constraints based on the actual physical laws from the knowledge store, and forced a complete re-implementation of the code.
That is amazing.
And then the global critics stepped in to verify a concept called zero-mode multiplicity, which is essentially checking the mathematical boundaries of the entire system before allowing the research note to even be drafted.
The agent basically peer-reviewed itself mid-stride.
Exactly.
It caught the impossible physics, stopped the presses, and fixed the code before it ever reached the user.
It's brilliant.
And because of that architectural rigor, the domain experts grading these outputs found that DelveAgent had significantly lower hallucination scores compared to Gemini.
By a wide margin.
Right, because it tied its claims tightly to the actual computed artifacts rather than just wildly extrapolating from an impossible premise.
It is profound success for the architecture. However, we have to be intellectually honest about the limitations here.
Of course.
DelveAgent did not magically solve the physical sciences. It didn't max out the benchmark. If you look at the experimental design category, it only scored 17.1%, which actually merely tied the baseline Gemini model.
Which is pretty low.
Yeah. Experimental design requires incredible amount of human intuition, the handling of sparse or contradictory evidence.
An implicit knowledge that is notoriously difficult to encode into AI.
Exactly. It's just really hard.
So it's not quite ready to replace human scientists entirely. There's still plenty of job security in the lab.
Undoubtedly.
Yeah.
But what DelveAgent did achieve is a fundamental shift in the type of errors the system makes.
Okay, what do you mean?
By implementing this specific architecture, they largely eliminated the basic agentic instabilities, the formatting errors, the blind march down dead ends, the basic unit conversion failures.
A silly mistake.
Exactly. The errors that remain are now much harder, finer-grained scientific fidelity challenges.
I see.
We've moved from, the agent forgot how to write a Python loop to the agent struggled to synthesize a novel mechanistic explanation from a highly ambiguous data set.
Which is a completely different ballgame.
It's a massive evolutionary leap in capability.
It really is an entirely different class of problem to solve. So bringing this all back to the daily work of you, the listener.
Right.
If you are an ML engineer or an AI researcher trying to build robust workflows, what is the ultimate takeaway from DelveAgent and PhySciBench.
I think is pretty clear.
Yeah, I think it proves beyond a shadow of a doubt that for highly specialized, rigorous domains like the physical sciences, you simply cannot scale your way out of the problem.
We really can't.
Adding 100 billion more parameters to a generalist model does not magically impart the scientific method. You need purpose-built cognitive architectures.
You need systems grounded in domain knowledge.
Exactly. Systems capable of dynamic replanning and armed with rigorous local and global verification.
The paper makes a highly compelling, data-backed case that architectural specialization is the most efficient path forward. If you structure the cognitive workflow to mimic a human research team, a planner, specialized workers, and a critical reviewer, you don't just achieve better results.
You achieve vastly superior cost economics.
Exactly.
Which leaves us with a fascinating and honestly a little provocative thought to ponder.
Okay, let's hear it.
We've seen that targeted architectural specialization like DelveAgent can beat a massive generalist model at a fraction of the inference cost in the physical sciences.
Right.
What does this mean for the future trajectory of AI agents across all industries?
It's a great question.
Are we finally moving away from the dream of one massive monolithic God model that does absolutely everything?
It seems like it.
And instead, are we heading toward a diverse ecosystem of hyper-specialized, deeply grounded, agentic frameworks that just talk to one another?
A network of experts.
Exactly. Will your future AI assistant be a single omniscient brain or an entire digital laboratory of specialized agents?
Something to think about as you design your next workflow.
Definitely. Thanks for joining us on AI Paper Slop.